All right, today we're diving into something that sounds like it's straight out of science fiction. It's a device, a helmet actually, that could completely change the game when it comes to treating disorders that are buried deep inside the human brain.
You know, for decades, if doctors needed to get to the deepest parts of the brain, it meant one thing: surgery. We're talking about drilling into the skull to implant electrodes. But what if? What if there was a way to do it with incredible precision, but without ever making a single cut?
So, to really get why this is such a massive leap forward, we've got to first appreciate just how hard it is to work with the brain. It's a real challenge.
Think about it. Buried deep inside your head, you've got these tiny, critical structures, like the thalamus. They're like the central command centers for, well, for everything, from how you move to your very consciousness. So when something goes wrong in there, the results can be just devastating. And a lot of these disorders are notoriously tough to treat with our current tools.
And that brings us to this classic medical dilemma. You've basically got two choices, and neither is perfect. On one side, you have deep brain stimulation, or DBS. It works. It's super effective because you're putting electrodes exactly where you need them. The catch? It's major brain surgery. Then you've got the other options, safer, non-invasive tools. The problem is, they're kind of like trying to hit a tiny bullseye from a mile away with a fire hose. They just don't have the depth or the precision.
So how do you get the best of both worlds? Well, that's where this new tech comes in. Let's talk about this revolutionary ultrasound helmet. This isn't something that just appeared overnight, by the way. It's the result of over a decade of work by researchers, and it's called transcranial ultrasound stimulation, or TUS.
Okay, so the basic idea behind TUS is actually pretty brilliant. Instead of scalpels, it uses sound waves, ultrasound to be exact. The magic is that these sound waves can pass right through your skull and skin no problem. And then they can be focused with laser-like precision to a single tiny spot deep inside the brain to either dial up or dial down the activity of the neurons there.
Now, to get that incredible precision, this isn't just one big speaker blasting sound at your head. No, the helmet is packed with 256 individual ultrasound sources. I love the orchestra analogy they use. Imagine each one is a musician, and they all play their note at just the right time so the sound waves converge on one single tiny point in the audience. It's the same principle.
And the result of this orchestra? A technological leap that is just huge. This setup can create a focal point that's 1,000 times smaller than what you could get with older ultrasound tech. 1,000 times! I mean, we are talking about a level of pinpoint accuracy from outside the skull that was pure science fiction until now.
But for all this futuristic tech, what's it actually like to wear? Well, it's pretty grounding, actually. One of the researchers, who was also a participant in the study, said it was chunky and claustrophobic when she first put it on. It's a great little reminder that behind all this amazing science, there are real people putting it to the test.
Okay, so you've got this amazing helmet that claims to have pinpoint accuracy. That's a bold claim. So how in the world do you actually prove that you're hitting a microscopic target deep inside a living, breathing human brain?
Well, the researchers picked a target that was almost impossibly small on purpose. They aimed for something called the lateral geniculate nucleus, or LGN. This thing is a tiny, tiny relay station for your visual system buried deep in the thalamus. We're talking about a structure with a volume of about 80 cubic millimeters. It was the perfect stress test. If you can hit this, you can hit anything.
And here's where their experimental design was so clever. Instead of trying to measure the effect right at the tiny LGN, they decided to look for the ripples. Think of it like this. The LGN is the light switch. The visual cortex is the big light bulb in the ceiling. So instead of trying to see the tiny switch flip, they just looked to see if the big light bulb turned on. They knew that if they stimulated the LGN, they should see a clear, measurable effect in the much larger visual cortex it's connected to.
So here's how they set it up. They had participants slide into an fMRI machine, which, as you know, measures brain activity. They put the helmet on them and aimed those 256 ultrasound beams right at the LGN. Then, while this was happening, they showed the participants a flashing checkerboard pattern, a classic way to get the visual system all fired up. The whole time, the fMRI was watching the visual cortex, looking for any changes caused by that ultrasound. All right, the moment of truth. Did it work? The answer is a big yes. And the results were even more interesting than they might have expected. It wasn't just a simple on switch. They found they could actually control the brain circuits in two completely different ways. Check this out. When they sent in the ultrasound pulses while the person was looking at the checkerboard, they called this online stimulation, the activity in the visual cortex shot up. It basically boosted the signal.
But then they tried something else. They sent a short burst of ultrasound before the task even started, the offline stimulation. And this did the complete opposite. It dampened the activity in the visual cortex. And get this, that dampening effect lasted for over 40 minutes. So it's not just an on-off switch. It's more like a volume knob and a mute button that has a lasting effect.
And here's the kicker, the part that really proved their precision. They ran a control experiment. They aimed the helmet just a little bit off target, at a nearby brain area. And what happened? Nothing. The effect in the visual cortex was gone. Totally gone. That's the proof right there. They were hitting exactly what they were aiming for, and nothing else.
So, okay, we know it works. We know it's incredibly precise. We know you can turn brain circuits up or down. The question now is, so what? What does this actually mean for treating real people with real conditions?
Well, honestly, this could be a complete game changer. We might be looking at a whole new way to do therapy. You're talking about treatments that are, 1, non-invasive, no surgery. 2, they can be reversible. The effects can be temporary. And 3, they are hyper-targeted to the exact brain circuit that's causing the problem. That's a combination we just haven't had before.
And the list of what this could be used for is just staggering. We're talking about new possibilities for Parkinson's disease, for schizophrenia, helping people recover from a stroke, treating chronic pain, depression. I mean, the list goes on and on. It offers a new ray of hope for so many conditions that have been incredibly difficult to manage. And looking even further down the road, the team behind this imagines a day when a version of this helmet might even be something you could use at home, maybe guided by AI. I mean, just imagine that. It would completely open up access to the brain, not just for treatment, but for understanding it. So it leaves us with this huge, fascinating question to think about. How does everything about medicine and health change when the brain is no longer locked away behind a wall of bone that only a surgeon can get through?